Hey Caleb, I got your email, so I'm going to do this video to try to run through this. I saw your equation there, or the question you had said to describe the conic, and it gave you an equation similar to this. So you'll notice that this is not the exact equation that you had, but it is very similar in structure. So I'm going to go through this one, and then you can see if you can take out what I'm explaining here and apply it to the question you had. So the first thing you want to do when you're looking at this equation of the conic is remember, for us to be able to pull out the information we need out of this equation and to be able to kind of interpret this equation, the main thing is that we need this first number to be a 1. Because remember that we want that equation to look something like this. In my case, sine of theta. Now in your case it was cosine, but again it'll work basically the same. So in this setup here, the key is that we want this front number to be a 1. And when that happens, then we can use everything else from the equation. All right, so over to the equation we have, I need to rewrite this thing so that that 3 becomes a 1. And the way I can do that is to go here and turn the 3 into a 1 by dividing everything by 3. So notice that there is a 1 right here right now. So if I divide that by 3 and then divide that by 3, then once you do that, then now the new version of that equation, 6 divided by 3 right here, would become 2 on top. In this area here, 3 divided by 3 will now become my 1. And then I would have minus 1/3 sine of theta. Okay, so now I can use that equation, because now that equation has that 1 in that position like I need from what we said over here. So with that being said, the next, oh, I forgot right here, there was supposed to be an E there. Sorry about that. So this number represents your E value, your eccentricity. So my E is 1/3. And thinking back to our notes, the E is going to tell you what kind of conic you have. And if you remember, when E is less than 1/3, or sorry, when E is between 0 and 1, then that's going to mean that it's going to be an ellipse. So because of that, we have an ellipse. All right, the next key piece to this is this combined with this tells me kind of the orientation of the ellipse. So let me come over here to the side, and let me go and get my axis, get my pen right. So I've got something like this. And sine, with it being sine, that's going to tell me that I have a horizontal directrix. So the fact that I have sine is going to tell me that I'm going to have a horizontal directrix. And the fact that this is subtraction means that it will go below the pole. Now the pole and the focus in this case are the same thing. So let me get this changed over real quick so we can kind of see what's going on. We'll go green. So I'm going to have my focus here at the pole. I'm going to have an ellipse. I'm also going to have a horizontal directrix below the pole. Now to know how much below the pole, then I need to consider the p-value. Now if you look at our top that we have here, our top is 2. And that 2 represents that top piece of my formula, which is EP. So that means that I have the top piece, or the numerator, 2, is E times P. And I know that E is 1/3. So I've got 2 is equal to 1/3 times P. And if I multiply both sides by 3 here, then I would get this 6, 3 and that cancel is equal to P. So this tells me how much below the pole. So it's going to be a horizontal directrix 6 units below the pole. So now that I know that, 1, 2, 3, 4, 5, 6, there's going to be my directrix line. Oh, come on, there we go. Got that. Okay, we're dealing with our ellipse. I'm just trying to keep everything in focus about what we're doing here. So I'm going to have an ellipse. Being that the directrix is down here and I have one of the focuses here, then remember what we were talking about yesterday is this is going to basically mean that I've got an ellipse doing something like that. It's going to be vertical. Remember, the shape will always be perpendicular to your directrix. So this finally gets into the question that you had, that you sent to me when you were asking about where are the vertices. So I didn't go straight to the vertices because I wanted you to see how you got to this point right here. On the question that you had answered, I see that you had indicated that yours was an ellipse also, and I see that my lab had told you it was correct. I see where you had put that you were going to have a vertical directrix, and then up under that, you had put in that your directrix lies 4 units to the right of the pole. So I'm going to go ahead and tell you a clue. You need to check that number 4. I don't think that is correct. I could be wrong, but I don't think that's correct. Tell you what, pause for just a second. Let me look at that. Okay, never mind. Scratch that. So I just figured I was doing it mentally before, but this time I actually did it on paper. And yeah, I think you're good there. So back to your question. Find the vertex over the vertices. All right, so with what I'm doing, if I know that the ellipse is vertical in my situation like this, then figuring out where the vertices are, I need to think about their angle locations. So think about that on the unit circle where this is 0, 90, 180, and 270. Well, being that my vertices are vertical, that means they're going to be in the 90 and 270 direction in terms of what I will put in for theta to figure this out. Okay, so let me get this back out of the way so we can actually do the math on that. There we go. So remember, I'm going to be using 90 and 270 into either this equation or this equation. It doesn't matter. I'm actually going to go with this original one that was in black because there's no fractions there, using 90 degrees and 270. So using 90 degrees, if I do that, if I plug 90 degrees in for my theta here, then I would have sine of 90 degrees. Sine of 90 degrees is 1. Then I would have 3 minus 1, which would be 2. And then 6 up top divided by 2 would be 3. So that means at 90 degrees, I would have an R value of 3. So if 90 degrees, R is 3, which means I would have a coordinate of 390 in polar form. All right, then to do 270, degrees, again, I'm going to take that and plug it in up here for theta. So sine of 270 is -1, which will be 3 minus a -1. That would be 3 plus 1, which is 4. 6 divided by 4 reduces to 3 over 2. So I would have a polar coordinate of 3 over 2 and 270 degrees. All right, so I think that's accurate. All right, so these are my 2 coordinates of my vertices in polar form. So I'm going to do the first one, 3 in the 90-degree direction. So here's the 90-degree direction, and I'm going to go up 3 units. So 1, 2, 3. There is my first vertex. The other one is saying 3 halves and 270. So 270 is in this direction, and I'm going to go down 3 halves. Well, 3 halves would be right here. So let me zoom this in a little bit. 3 halves is 1.5. Okay, so this is a focus. This is a vertex. So then I'm looking at something like that. Would be my actual ellipse. All right, so there you go. In this question, let me just look real quick. It says type an ordered pair. Yeah, so if I'm doing this as my coordinates, this one would be 390. If I'm doing polar, if I was doing X and Y rectangular, then it would be 0, 3. And then the one here in polar would be 3 halves, 270. If I was doing rectangular, it would be 0 and -3 halves. And that is your vertices, or those are your vertices. All right, hope that helps. If you have any questions, send me an email.